Okay, so today we are going to discuss the problems on hydraulic gradient line and the total energy line. So our first problem is to determine the rate of flow of water through a pipe of diameter 20 centimeter and length 50 meter when one end of the pipe is connected to a tank and the other end of the pipe is open to the atmosphere. The pipe is horizontal and the height of the water in the tank is 4 meter above the center of the pipe. Consider all minor losses and take F is equal to 0.009 in the formula. HF is equal to 4FL V square by 2GD. Draw the hydraulic gradient line and the total energy line. So what have they asked? They have asked for to determine the rate of flow and also to draw the hydraulic gradient line and the total energy line. So first of all, we'll have to draw the figure, isn't it? Because the figure always carries marks. And what have they said? They've said that a pipe is being connected to a tank, right? So we have to mark the figure like this. And I've marked the diameter of the pipe as 20 centimeter. I've marked it in meters also. And this is the length of the pipe, which is 50 meter. And they have said that the height of the water in the tank is 4 meter above the center of the pipe. So this is that center of the pipe, isn't it? This is that center of the pipe and the height of the water in the tank is 4 meter above the center of the pipe. So you have to mark it like this. That is this 4 meter up to the free surface of the tank. Okay. Now, what have they asked? They have asked for to determine the rate of flow. Since they have not given any velocities, etc., we'll have to apply the Bernoulli's equation at 2 points in this tank and pipe in order to compute the rate of flow. Okay, so applying the Bernoulli's equation, see, the Bernoulli's equation should always be applied at 2 points, right? So the points to be considered is one at the free surface of the tank and the other at the outlet of the pipe. Why are we considering these 2 points? So that we can get a very simplified Bernoulli's equation. Okay, so let's see how we can get that. So if you are taking the first point at the free surface of the tank, that is at this point, we know that Bernoulli's equation is P1 by rho g plus V2 square, V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus all losses. Okay, they have asked us to consider what all losses? They have asked us to consider all minor losses and also the major losses. Okay, that is the frictional loss. So this is our equation. Now, at this point, coming to this point, that is at the free surface of the tank, we know that P1 by rho g will be 0. Why? Because this point, this tank is open to the atmosphere, right? It is given in the question that the tank is open to the atmosphere. That is a key point. Okay, open to the atmosphere means it will be under atmospheric pressure, and I have said that for our calculation we are always taking atmospheric pressure as 0. So we get P1 by rho g as 0 because P1 is equal to 0. That's why. And V1 square by 2g is also 0 because why? Because this is a tank, right? This is a tank and water won't be flowing in a tank and the velocity here at this point will be very much less than the velocity in the pipe, right? Because obviously the area of the tank is very much more and area of the pipe is very much less. So comparing these two areas, the velocity at this point will be very much low and the velocity at this point will be very much high in order to adjust the discharge. So we can take at this point the velocity as 0 because practically there is no flow at this point. Only the water or the fluid is flowing only through the pipe, isn't it? So we can take V1 square by 2g as 0 and Z1 we are taking this point, that is the center of the pipe, as the datum. So what will be Z1? The height from that datum, isn't it? The head from that datum. So at this point the datum will be 4. So we can take Z1 as 4. Now coming to this point, that is the outlet of the pipe, here also the pipe is being discharged into the atmosphere. Okay, other end of the pipe is open to the atmosphere. It is set so. So it is being discharged into the atmosphere. Obviously this point will also be the pressure will be atmospheric pressure. Therefore we can take P2 as 0, that is P2 by rho g as 0 since it is under atmospheric pressure. That is the outlet of the pipe. And what about V2 square by 2g? Obviously it won't be 0 because the fluid will be flowing with high velocity throughout the pipe. Okay, And what about the datum? We are taking this as the datum, right? The height from the datum is 0 at this point. At this point it was 4, the outlet of the pipe, since this is our datum, the center of the pipe is our datum, obviously Z2 will be 0, and all losses, that is, we know that there is the major loss, that is the frictional loss happening through this pipe, that is HF, that is 4FL V square by 2GD, and there is an inlet loss here, isn't it? Because we know that minor losses occur at inlets or entrances, or due to sudden expansions or sudden contractions, and in this question we could only see the inlet loss, right? At this point there will be a small loss or a minor loss occurring in order to adjust the flow. Okay, so there are two losses, one minor loss and one major loss. Now substituting everything, what will we get? 4 is equal to V2 square by 2G plus HI plus HF. Okay, now what is HI? That is the inlet loss is 0.5 V square by 2G. Here V is actually V2, that is the inlet velocity. Okay, we should take the inlet velocity. And what about the frictional losses? We know the formula is 4FL V square by 2GD, and here also V is V2, isn't it? The frictional loss is happening throughout the pipe when it's flowing through the pipe. So we have to take V as V2 here also, and V1 is obviously 0. And so we get our equation like this, in this form, that is 4 is equal to 4 V2 square by 2G plus 0.5 V2 square by 2G. This is our minor loss at that inlet. And 4FL V square by 2G, that is 4 into F. It was given in the question as 0.009, and length is the length of the pipe, 50 meters, and V2 square by 2G into D, right? 2GD. D is the diameter of the pipe in meters. Okay, so after solving this equation, since this every term is in terms of V2, we can solve for V2. So we got V2 as 2.734 meter per second. Okay. Now what have they asked? They asked us to determine the rate of flow, isn't it? So rate of flow or discharge is equal to area into velocity. Now we know A2 is the area of the pipe. Therefore pi into 0.2 square by 4 into V2. We have now found out, right, 2.734. So we get the discharge as Q is equal to 0.08589 meter cube per second. If we want, we can convert it to liters per second. Okay. Now they have also asked us to draw the hydraulic gradient line and the total energy line. So what is this hydraulic gradient line and the total energy line? Hydraulic gradient line is the line joining the summation of the pressure head and the datum head, and the total energy line is the line joining the summation of the pressure head, the velocity head, and the datum head. Okay, so in order to draw this hydraulic gradient line and the total energy line, we'll have to draw this figure again. Okay, so I've drawn the hydraulic gradient line and total energy line here. So this is our figure. We should draw the figure again. And what should we do? We have to consider at least 3 points. Okay, considering 3 points at the free surface of the tank. That is, A is the free surface of the tank, B at the inlet of the pipe at this point, and C, that is at the outlet of the pipe. Okay, now we have to consider 3 points like this. Now what to do? We have to compute hydraulic gradient and total energy line. Okay, so coming to the total energy line, HA, we know that obviously P1 by rho G is 0, and V1 square by 2G is also 0. Okay, and only Z1 is there, right? Only Z1 is remaining. So the total energy line will be what? We know total energy line is P1 by rho G plus V1 square by 2G plus Z1. So since the other two terms are 0, only Z1 is remaining. Our total energy at this point, that is at the point A, will be equal to 4. So we have to mark that point, that is at this point it will be 4. Okay, that at this point it will be 4. Okay, and at B, what's happening? At B, what's happening? At the inlet, we know that there's a small minor loss, isn't it? That is the inlet losses. We have to subtract that inlet loss from this total energy at A. That's what we have to do. Since at this point it was 4. Due to the minor losses, there's some loss of this total energy, isn't it? So we have to subtract that from 4. Therefore 4 minus that, the in that loss is 0.5 V2 square by 2g. 4 minus 0.5 into 2.734 square by 2g, we'll get it as 3.81 meter. Okay, we get the total energy at B as 3.81 meter. That is at this point. Okay, I am marking it as D and E. Until D it was 4. Due to the inlet loss at this point, there is a small drop in the energy. That is this is the head loss due to inlet, that is 0.19 meter, and mark it as E. Okay, so up to this point from the datum, the height will be, or the total head will be 3.81. That's what we got here, right? And next is what? Next we have to compute the at point C, that is at the outlet of this pipe, isn't it? At the point C. So at that point, we know that the total energy is P2 by rho g plus V2 square by 2g plus Z2, and P2 by rho g is 0 obviously because it is open to atmosphere, and Z2, since this is our datum, center of the pipe is our datum, Z2 is 0. So we got total energy at C as 0.38 meter. Okay, but what's happening? From B to C, at this point to this point, there is major frictional losses, isn't it? So we cannot just jump directly to this point, right? There is obviously a loss, some amount of head is lost due to the friction. So we have to compute that head loss, and how much is that? It is 4FL V2 square by 2GD, which is equal to 3.428 meter. Okay, this much of energy or this much of head is lost from B to C. Okay, now what happened? We have to mark this here also. So until here we reach till here, right? So this head lost we have to mark, that is 3.428 is lost from here. So 3.81 minus 3.428, what will we get? It will be 0.38 meter. Okay, yeah, so you have to mark it here, that is as the point F. Now we got the total energy line. So DEF is our total energy line. Okay, now similarly we have to draw the hydraulic gradient line. So one point to remember is that the hydraulic gradient line can be always parallel to the total energy line. Okay, at this point we have drawn a parallel line, isn't it? So why this line, total energy line, is slanting? Because there is a head lost. Okay, that's why. Now hydraulic gradient at A, that is at this point, what is the hydraulic gradient line? What is hydraulic gradient actually? It is P1 by rho g plus Z1. No velocity head is considered here. Okay, it's also known as piezometric head. So we know that P1 by rho g is 0 and Z1 is 4, right? So at this point, that is at the point A, the hydraulic gradient at A is always 4. So this green line I've already marked it at, I marked it at 4 itself. Okay, so we have to originate the hydraulic gradient from this point itself, that is the 4 meter from the datum. Now the hydraulic gradient at B, that is at the inlet. So at the inlet we know that hydraulic gradient is P1 by rho g plus Z1. This we can find out by subtracting the velocity head from the total energy, isn't it? So what I'm doing here is, we got the total energy at B as 3.81 considering all the losses etc. So how to get that hydraulic gradient at that point? Just subtract the velocity head at that point. Okay, from so 3.81 minus V2 square by 2g, will get it as 0.38. Okay, so at this point, that is at the point B, what's happening? The hydraulic gradient is how much? 3.43. Okay, now we have to mark it as G. I've marked it as G. Okay, from the datum we'll get it as 3.43 and mark it as G. So there is a drop, isn't it? Hydraulic gradient was 4 here, and then due to all the losses and subtracting the velocity head, there is a drop of hydraulic gradient. And how much is that? From the center it is 3.43. And what else? And we have to compute the hydraulic gradient at the outlet of the pipe also, isn't it? So how to compute that? Obviously, we know that hydraulic gradient at C will be P2 by rho g plus Z2. P2 by rho g is 0 and Z2 is also 0. So, always the hydraulic gradient at the outlet will be coinciding with the center of the pipe. So, just mark it as the point C at the center of the pipe, that is it is 0, okay, because it is coinciding with the datum. Now just draw it parallel to the total energy line as a slanting line, okay. So this is how we draw the total energy line and the hydraulic gradient line.